Recording. So if you weren't here, what is today? Tuesday or Wednesday for B2 day. This is what we talked about. So I have an invention. It's called the coffee Can-Dil. This is actually what it is. What I have here is it's a Maxwell House coffee can that I put a hole in the bottom, which is actually the top. And then there's another little hole on the side here. So what I do is I fill it up with methane gas. So I fill it up with methane. Let's see, methane. Oops. Oh no. So fill it up with methane right out of the gas jet. So I light it on fire. And what happens is, and so it's too bad that you weren't here and you missed it, but what happens is when I light that sucker on fire, we get a nice orangish yellow flame. So let me see here. Orangish yellow flame. So right here then, I've got this nice orangey yellow flame, about 5-6 inches tall, that comes out the top. And so again, my invention, like if the power goes out, then you could maybe have a few of these hanging around. You can fill them with some methane, also known as natural gas, and you can have yourself a little source of heat and light, and everybody would just love it. Except the fact that after it burns for just 30 seconds or a minute, the flame gets really small pretty quickly. And the flame is no longer orange. It actually changes to kind of a light blue color. So we've got this littler flame, a blue flame, that's not nearly as tall as what it was before. And again, I really wish you had been here, but several minutes after that, the flame is so small, you can barely even see. And most students can't even see that there's still a little tiny flame in the opening. And then at the very, very end, kablooey, the can blows up. So I kind of have a problem with the invention. And that led to some discussion about, what's going on here. So we were talking about using particle diagrams to explain what's going on inside the can during this whole thing. So what do you think is in the can at the start? Well, I told you, right? So what's in the can? Methane, right? It's on the screen. So methane's in the can. Now, how can I represent the methane in the can? Methane is a gas, right? It's not liquid, so it's a gas. So how do I show that in the can? Well, I'm going to just, pull rank here and just sketch it on there the way I would sketch it. Because again, we're talking about a particle diagram, okay? We're talking particle diagram is what we're looking at here. So I'm going to say that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. How about that? 28. I got 28 particles in here. And I'm going to put a key here so that people know when they look at my diagram, they know that those little green circles are methane gas. So that's what's in the can, right? And it's burning. And it produces a nice tall orange bright flame. But then about halfway through, what do you think's going on here? And so what we talked about in class is that as the methane is coming out and burning, and we also did some testing and found out that methane actually floats. And we knew that because there's actually another little hole in the side of the can here that most people didn't really notice that I had to point out. And I tried to light the flame down at that bottom corner. So I tried to light the flame down here and it wouldn't burn. It would only light up here. And when I held the lighter well above the can, it would light. Meaning the methane has to be doing what? If I'm holding the flame up here to light it on fire and it lights from way up here, that means the methane's rising out of the can, which means it floats in air. Otherwise, it would sink in air and it would fall out the bottom and I could light down here. But it won't light from down here. It will only light from the top. So that's an important fact, an important observation about this whole thing. So that means the methane's floating up out of the can. So over here, what do you think is probably true of what's in the can? Is there more methane, the same amount of methane, or less methane in this can? I hope you're thinking less, because what's been happening? It's been burning. This is like a minute or more later after we lit it, then it looks like this. So there's less methane, flame is smaller, right? So, another question, where do you think most of the methane is concentrated? Most people in class were saying near the top of the can, because if it floats, then it's going to be floating to the top. So I'm going to draw it that way. So but there's less. I had 28. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now notice. So I put about half of them in there. Notice though, they're not all at the top, but most of them are at the top because methane floats. But maybe there's some stragglers around there. I don't know. And again, we're making this up. Like, I can't see the methane in the can. Even if the can was clear, I couldn't see the methane in the can. Methane is an invisible gas. You can't see it. So we're just kind of taking a stab at it. We're looking at what happened to the flame, you see. We're looking at what happened to the flame, and we're trying to describe what may be happening that we can't see that would make sense of what is happening here. So here, a lot of methane. It's all coming out pretty quickly, burning a lot. Here, there must be less methane because the flame got smaller, but it also changed color. So, do you think there's anything else going on? Could there be something else in the can? If methane is leaving, do you think something has to go in to the can to take its place? If you said yes, then you'd be right. And what do you think would have to go in there? Like what's in the room, right? Air, I would agree. Air is probably going in to take the place of the methane that's coming out. And someone in class suggested that that's why the flame changed colors. Makes sense. So the flame got smaller because there's less methane here. It turned colors because maybe air got in and is mixing with the methane. Oh, seems logical. Now, do we have any way of proving this? No, but it is a logical explanation to explain what we observed. So, how am I going to show air particles in there? Well, I'm going to make them a different color. And I'm going to say that air is going in. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now notice I have as many air particles that I put in there as what I had methane particles that left. I started with 28 here. I got 14 methanes left. I got 14 air particles that went in. I don't even know if that's true. I'm just making it up, but it seems right. Now notice most of my air particles are near the bottom, maybe a couple stragglers in the top. Most of my methane particles are in the top with a couple stragglers in the bottom. Is that really the way it is? I don't know. Are they more divided than that? I don't know. But if methane floats in air, you would think that more methane would be at the top of the can. I mean, I don't know. We don't know what's in that can and exactly how it looks. Now, I should probably add something to my key then, since I have air particles now in there. I'm going to add over here, hey, if you see a little red particle, that's air. Now, at the end, you see the can blew up. The can blew up. Okay, well, so at that point we had kablooey. We had all kinds of explosion, right? It exploded. Now, Notice I did not draw particles here for the explosion. I just did a bunch of squigglies. Well, I don't know. Do you think fire has its own particle? And then we talked a little bit about that in class. Like, do you know what methane actually is? Like chemically. Well, it's CH4 is what that is. Do you know what air is? Well, it's mostly nitrogen and some oxygen, and then some other stuff that's small percentage. 78% nitrogen, 21% oxygen, and then 1% other gases. So we have methane, and then we have N2 and O2. That's what air is. So air is that stuff. N2 and O2. So do you think there's an actual fire particle? I busted out the periodic table of the elements. And so do you think there's an actual particle that is called a fire particle? They used to think there was. They used to think that there was a fire particle called phlogistogen. Because if you have oxygen, nitrogen, all the gens, and so then maybe phlogistogen would be a fire particle. And so then they would have drawn, little fire particles here, and then maybe different fire particles because they're different color here, and then maybe other fire particles here. Now, one thing I did see in class, when one of the cans blew up, it literally flipped around, and I could see a burning ball fireball inside the can. So there was burning going inside the can when it blew up. So then the theory was, or the question was, what happened? How did this happen? And so one of the theories was that the flame here got so small that it actually fell inside the can, igniting any methane that was left in there. And then when things burn, they get hot. And when air gets hot, it expands. At least that's what people were saying. And when it expands, it has to have some place to go. And so, boom, it blows the lid right off, or blows the can off the lid, and then it goes up. So, do we know for sure that's what happened? Well, I don't know that there's any way we can know for sure. That seems to make sense for what we observed. Okay, so a lot of what is going to happen next is that we are going to be making some observations. We will be collecting some data. Sometimes the data is just our observations. Sometimes it's our observations and some quantifiable data. Quantified means numbers, right? So a quantitative collection of data is all the numbers. A qualitative collection of data is like what we're doing here. This is qualitative. There aren't like actual numbers involved. We're describing what we saw. We're making some diagrams based on what we observed. That's qualitative. Quantitative means we have real numbers of actual data. So we'll be doing both. We'll be having some qualitative data and some quantitative data along the way. But we will be using particle diagrams for all of this. Particle diagrams are going to be a major part of what we do. And so there are a few rules for particle diagrams. I want you to write these down. Hopefully you sketched all this already as well. But some particle diagram rules. Let me get this stuff out of the way. Let's see. Let me move. Oh gosh, all that stuff was being hidden. Probably by my face on the video. I apologize. Particle diagram, air. Oh my gosh, air is N2 and O2. So particle diagram rules. Here we go. 1. Make it quick. Do not waste a bunch of time. This is not an art project, okay? No art project here. So make it quick. Do not waste a bunch of time. Like, it did not take me long at all to draw those particle diagrams, okay? So don't waste a bunch of time drawing it. 2, use colors. Oops, I can't write. Use colors or shapes. Colors or shapes for what? To distinguish between the different kinds of stuff. So we had methane and air. I need to show those as different. If you don't have different colors, then you should use different shapes, like squares and circles, or triangles and squares, or triangles and circles, or whatever. Something. Stars and circles. I don't care. And 3, because you do that, you better have a key. include a key that tells people what's what, like I did here. And fourth, remember to title it so we know what the heck the stuff is. So title what you have going on so that we know what the heck it even is. All right. That's kind of what we put together today. Hopefully that makes at least a little bit of sense. That's what you missed. Then we started talking about the lab that we're going to be doing in class, which is on Classroom, the actual form with all the directions of what you're going to do. So that is going to be done on Thursday and Friday for the B1 and the B2 groups. So Thursday and Friday, we will collect all that data, and then I'll tell you what to do with it once you collect it. But the lab itself, the PDF file, is posted on Classroom. We will only be doing sections or parts 1, 2, 3, and 5. We're not doing the part 4 with the ice cube because it's you can't fit the ice cube in the vial. So that's what we're doing. This is what we did today. Hopefully you're doing well wherever you are, and hopefully we'll see you soon.